In this work, we present the Micromachined quartz resonator array and principal component analysis to cluster the species and concentration of volatile organic compounds. This work used the Micromachined quartz resonator array to acquire the data. The resonator used a high resonance frequency of 49 MHz. They were coated with 4 different function materials. The materials were printed with a commercial piezoelectric dispense system with coating thickness of 100 nanometers. The experimental setup consisted of synthetic air and aniline gases in cylinders as gas source, a bubbler to provide humidity, and mass flow controllers to control flow rate and resulting desired gas mixtures. The mixture was sent into a custom-made chamber with the sensor array connected to an RF multiplexer. A network analyzer was used to collect data. Acetone, ethanol, and toluene were tested as the gases. The gases were mixed with synthetic air and humid air to reach a 20% relative humidity and targeted gas concentration inside the chamber. Before each testing, the resonator was regenerated. During testing, different concentrations of aniline gases were exposed to the resonators. Sweepings of conductance of resonators were acquired and analyzed for the resonant frequency shifts. The testing results showed that the resonator showed frequency shifts with aniline gases with a response time of less than 60 seconds. For each exposure, the frequency shift in Hertz was extracted and linear fitted to calculate the sensitivity of the resonators to the aniline gases. It showed that different polymers responded differently to 3 aniline gases. Principal component analysis was used on the data points of the frequency shift of all the combinations of gas species and concentrations. 2 of the most significant components were calculated and plotted on a graph. The results showed that the data points belonging to 3 aniline gases were clearly separated in distinct clusters. This enables the classification of the species of an unknown gas regardless of the concentration. Next, the 2 components were transformed with a formula to obtain 2 new parameters, and the data points were plotted with these parameters. The results showed that the data points belonging to different gas concentrations were clearly separated in different clusters. This can determine the concentration of gas. In summary, we have demonstrated a Micromachined quartz-based gas sensing platform with a quick response time and the ability to determine the species and concentration of an unknown aniline gas using principal component analysis. To know more about our work, visit our poster.